So hello everyone, my name is Jana and I'm an applications engineer here at Heidelberg Instruments Nano in the Zurich location. And during this webinar, I will talk to you about the NanoFrazor technology, and I will show you how it can enable advanced nano devices and also very unique applications. So I will start off this talk by giving a quick introduction to the NanoFrazor technology, and also I'll be explaining its high-resolution patterning capabilities. Then I will go over the different pattern transfer possibilities that we use in combination with the NanoFrazor writing. And finally, I will showcase some applications and also show you some device fabrication examples that are truly unique to this NanoFrazor technology. At the end of my talk, which will last approximately 30 minutes, we will have a Q&A session. If you look at the webinar, platform here in front of you, you can enter your questions in the questions/chat window. And just as a quick note, only the organizers can see your questions. And at the end of the talk, I will be going over them and hopefully answering all of them. All right, so let's dive right in. So what is the NanoFrazor? It's a thermal scanning probe lithography technique. It uses an ultra-sharp tip for both the writing and the reading of nanoscale structures. Here you see both examples. So you can think of using the NanoFrazor whenever you need artificially made nanostructures on the surface. And in this case, we are using heat as a trigger. So in the writing mode, we are heating up this cantilever tip, and in the reading mode, we are cooling it down. And because we are using heat as a trigger, we work with thermally responsive substrates underneath. And in the standard mode, in particular, we're using the NanoFrazor with thermally responsive resist. In this case, when the tip gets in contact with this thermal resist, it's directly sublimating it. So unlike typical lithography methods like photolithography or e-beam lithography, there is not a need for a subsequent wet development step after the writing. Here, the resist is directly being sublimated by the tip. And here we are talking about features in the 10 nanometers lateral resolution range, and also 1 nanometer vertical resolution range. And when operated in the cold mode, the same cantilever tip can be used for reading the very same nanostructures that were written in this thermal resist. So there's no need for a separate metrology step after the patterning to inspect what you have written. And I have to mention as well that the heating and the cooling of the tip happens in the microsecond range, but we will go into more details on this a bit later on. More recently, we have also integrated a laser writing head into our systems. And what this does is it allows for 100 times faster writing or even more. And in this case, we are talking about more large area writing, and the resolution is then, of course, a bit more limited. So it's a lower resolution method for writing, and here we're talking about micrometer scale features that you can write. But what's really cool in this case is that the same laser writer head, the laser writer head can work with the same resist system. So again, with the same thermal resist that we mentioned previously, and it also sublimates it in the same way. So no separate wet development step is required. So now that you have a quick idea of what the NanoFrazor technology is about, let's have a quick look about its background and where it's coming from. So the NanoFrazor technology has been commercially available under the brand name of Heidelberg Instruments only since 2018. And before that, it had its origins from a Swiss startup called Litho, and through a strong collaboration with IBM Research in Zurich, and also originally through the IBM Millipede project, which lasted for quite some time. In 2018, Societo joined Heidelberg Instruments, and currently we are about 20 employees in Zurich pushing the NanoFrazor technology forward. So currently we also have two types of NanoFrazor systems. So we have the NanoFrazor Scholar, which is a tabletop system. It allows for the reading and the writing with the cantilever tip only, which I've showed previously. But it's quite compact in size and suitable for smaller labs. But we also have the NanoFrazor Explorer, which you see here. And this one includes the direct laser writer head that I've mentioned. And it has a much larger enclosure also to protect the users from the laser beam. And having said that, these two systems are, you can use them in ambient conditions, so there's no need to place them in a clean room environment. You can place them in any office space. But having said that, the NanoFrazor system itself is also compatible with a glove box. So we can take the NanoFrazor Explorer or even the NanoFrazor Scholar, put it in a glove box and have it be integrated in a larger cluster of tools. In this case, the glove box is mostly useful for applications like 2D materials and 1D materials such as nanowires and so on, because these are quite sensitive materials that cannot be exposed to oxygen. Here you can see a distribution of the different systems that we have worldwide. At the moment, most of our customers are academic customers, but we are expanding more and more into industry and attracting more attention from industrial partners as well. And every time we install a NanoFrazor machine, we also like to take an image of the users, and you can see some examples here. So let's dive a bit deeper into the NanoFrazor technology. Here you can see the three main components that make up the NanoFrazor technology. So as mentioned, the key concept is to use a heatable silicon cantilever tip for nanopatterning features, namely features on thermally responsive substrates, thermally responsive resists, and in most cases, we are using PPA as our thermal resist because it sublimates quite fast by using heat as a trigger from the tip, and it sublimates cleanly as well and does not induce any or very limited contamination on the tip. Here we have two main PPA vendors. So we have our PPA vendor, which is based in Europe, All Resist, and another one based in the US, Polymer Solutions. And we are namely collaborating with Polymer Solutions to optimize the PPA resist that we are using for our processes. So other than the tip and the resist, what's very important about the NanoFrazor principle is that we are combining the writing and the reading. So by heating up the tip, we are writing on this thermal resist, and by cooling it down within microseconds, we are reading what we have just written. So in this way, we are performing lithography in a closed loop fashion. And I will go into a bit more detail about this in the next slides as well. Here you can see an overview about our thermal cantilevers. So you can see that they are completely made out of silicon, and they integrate a resistive tip heater. So this lies on top of the cantilever tip, and also a topography sensor, which sits on one of the legs of the cantilevers. And in this way, we can do both the reading and the writing simultaneously. And for more details about this, feel free to ask me in the Q&A session. I can explain more how the cantilevers are operating. But what's noteworthy here is the actual tip radius. So it's much finer than typical AFM tips, for example. So here we are talking about a tip radius of less than 2 nanometers. And ultimately, it's this tip size which will be limiting the writing resolution. So it's very important for us to have very fine tips. And we've optimized our tip fabrication process to achieve such small radii. Here you can see an example of how the writing works. Let me just click that for you. There's a video that illustrates the writing. Excuse me, I have to remove the laser pointer apparently. Just a second. There we go. So thanks to our integrated topography sensor, we can simultaneously read and write features. And in doing so, we perform what we call closed loop lithography. So here we pattern, we image, and we also provide live feedback for the next line in order to adapt the patterning. So here you see an example of a grayscale image, and you see how the tip is patterning this grayscale or multi-depth image into the thermal resist. And in the cold mode, the tip is reading what it has just written. And in case the depth is not at the target that we would like it to be, it provides live feedback to the software and then autocorrects for the next line. And what's really cool is that you can see this live topography image being built up on the software as you are writing. So in the end, it's really what you see is what you get with the NanoFrazor, and you are seeing the pattern being realized in a live manner on the software GUI. And because of that, you do not need a separate inspection after the lithography, and ultimately this is decreasing the total fabrication time of your devices or applications. So if we want to create nano devices, we can't just be writing on a resist. We also have to find a way to transfer these high resolution features from the resist onto the layers of choice underneath. And in the next slides, I will go over some different transfer techniques that we use in combination with this NanoFrazor patterning. One of the simplest methods that we use is called the bilayer lift-off method. So this is a method which is suitable for smaller labs because you only require, other than the NanoFrazor, only solvents to develop your devices completely. So there's no need to have dry etching tools, for example. Here you can see the process steps of the bilayer lift-off method through cross-sectional schematics. So the first step is to pattern the top layer of PPA, which lies on top of a lift-off resist, hence the name bilayer resist stack. And once that is patterned, we move the sample outside of the NanoFrazor and we perform the rest of the steps. So only this first step is realized in the NanoFrazor, and then outside of the NanoFrazor, we perform a wet etching step in order to transfer the pattern from the top thermal resist onto the layers underneath. And afterwards, you can coat a metal or a dielectric layer or any material through evaporation or even sputtering, and then lift off this resist layer underneath. And here, typically for the lift-off resist, we are using PMMA, which is quite common in many labs, and the lift-off can then be done with a very common solvent like acetone. And because this method does not use any oxygen plasma or dry etching techniques, it is compatible with sensitive materials such as nanowires or 2D materials. And it's capable of achieving quite high resolution features. So reproducibly, we can get features down to 100 nanometers with this method. The limitation, however, is the density of these features. So if you look at the cross-section of some lines that were etched down with this wet isotropic method, you'll see that there's quite a large undercut. So if we were to bring these lines any closer to each other, the top layer would collapse. So you can think of using this method whenever you want features that are around 100 nanometers in size and that are not so densely separated. Having said that, with a bit of feature tweaking, for example, if we're talking about bow tie electrodes that are exemplified here and also here on top of the nanowire, we can bring down this resolution to even 20 nanometers. So depending on the geometry of choice, we can push the resolution limit of the simple method even more. Now, if you want to have much higher resolution features and also more complex or arbitrary shapes that are more densely arranged, then a different resist stack is required. In this case, we would need to incorporate a hard mask into this resist stack. And if we're talking about high resolution liftoff, this is how it would look like here on the left. In this case, because we want a much higher resolution features, we need to thin down the PPA. And this is due to the conical shape of the tip. So the deeper the cantilever tip goes into this thermal resist, the more resolution we lose. So if you want really high resolution features, we need to thin down the top resist layer. But because of this thinning down, we can no longer use PPA as a mask to transfer these features. We need to incorporate another thin hard mask layer. In this case, we can use silicon dioxide, for example, and we offer solutions for this thin hard mask. For example, spin-on glass, which can be used just as a regular resist. It can be spin-coated and hard-baked and turned into a oxide layer. So then what happens in this case is that we start off again by patterning with the NanoFrazor, and then we take our samples outside of the NanoFrazor machine, and here we would require some dry etching methods to transfer the layers. So typically we use reactive ion etching. We open the hard mask and then we transfer the pattern through the bottom organic transfer layer. Again, here it can be standard PMMA. And for the case of liftoff, a layer can be deposited, metal, or even dielectric, as you see here. And then we perform liftoff as we did before with a simple solvent. Here you can see examples of what we can achieve with this high-resolution liftoff method. You can see examples of plasmonic antenna here that were done with gold liftoff. You can see that they are quite densely arranged. Also, we've had magnetic ellipses formed through the electric liftoffs, and also different electrode lines that were even overlaid on top of existing features. Now, we don't always want to perform a liftoff method, so we also have another pattern transfer technique. This one is used to transfer the patterns from PPA and amplifying them onto substrate materials of choice. So in this case, we are talking about a high resolution etching method, and the resist stack that we are using is similar to the one shown in the previous slide. So again, a shallow PPA to ensure the maximum resolution from the NanoFrazor writing, a thin hard mask, and an organic transfer layer. And again, once the patterns are written in the thermal resist, we take our sample out and we use a dry etching method like the RIE, and this time we are transferring the PPA patterns downwards. And using this method, we can have high feature density as well. We've had half-pitch lines of 14 nanometers, also holes that are 50 nanometers in diameter, or pillars formed of different materials. And this etching technique, it can be reactive ion etching or even ion beam etching. We've had good results with either. All right, so this is what it looks like if we're talking about 2D high resolution etching. But what's unique about the NanoFrazor is that it can also create 3D structures. and grayscale images in the resist. And you can see examples of this here. So what you see here is multi-depth, or what we call grayscale lithography. In this case, you can pattern in a much thicker thermal resist, and the limit to how deep we can go in the thermal resist is about 250 nanometers. And then we can transfer these patterns to dry etching again, or we can use the pattern in PPA or in another resist material and do template stripping directly from the PPA used as a mold in this case. And this is how you can also make this method compatible with more large area and large scale fabrication methods such as nanoimprint lithography. You can see cool examples of what we can achieve with this 3D high resolution etching here. We can get arbitrary shapes etched into substrates like silicon. For example, here you can see an optical Fourier surface that was created with the NanoFrazor. We can create also face plates, and you can see here a topography image which was taken in situ in the NanoFrazor machine just after the patterning of the PPA, so in this step. And then in the next step, you can see how it looks like once it's etched into the silicon with this SEM image. And if we take a cross section across this faceplate, we'll see that the target depth is around 6 times what we patterned in PPA. So we've amplified it by 6 times through the etching method. Here you see more examples of what we can achieve with this grayscale lithography. So we can have continuous patterns like the sine wave here, holograms and blazed gratings as well. And we can also achieve discrete levels of patterning in the PPA. And if you look at these plots here on the right, you'll see that the target and the written depth match quite closely. So here we are talking about errors of less than 1 nanometer. So using this high resolution grayscale lithography method, there has been many examples that were published in scientific journals. For example, holograms. Here at the top, for each of these examples, you'll see how the pattern looked like in the NanoFrazor. So this is a topography taken from the PPA, and then an SEM image of this pattern etched into the substrate of choice. In all of these cases, it is silicon. So at the top, you see many examples in the photonics industry, but you can also use this method for more biology-related applications, such as these two listed below. Now, if you want to focus on one of these and go a bit into more detail on how it looks like. So here you can see step by step how this 3D hologram was done. First, starting with the input design. If you look closely, you'll see that this design is made out of 8 discrete topography levels. So this can be a bitmap that you load onto the NanoFrazor tool. And then if we move on to the next step, you'll see how the patterning into the PPA was done and how it exactly follows the target design. If we look at this cross section here, you'll see how nicely discretized these eight topography levels are. And in this case, what we are using is a 90 nanometer thick PPA. And if we look at how selective the silicon etch is compared to the PPA, we know that there's a factor of 10 in there. So with around 90 nanometers of PPA, we can achieve depth of silicon up to 700 nanometers after the dry etching. And you can see how it looks like here through this SEM image. So we achieve an an amplification in depth of over 10 times. If we focus on this small area here, you'll see this pillar, which has quite a high aspect ratio. So here we're talking about a pillar with a diameter of about 65 nanometers and height of 700 nanometers. Now, if we wanted to amplify the patterns even more in silicon, it is also possible. But in this case, again, we can't only use PPA as the hard mask. We would have to introduce some layer underneath. For example, a thick PPA and then a thick oxide layer underneath. In the first step, you would transfer the design into the PPA, and then from the PPA onto the hard mask, and then again onto the silicon, and this time micrometers of silicon can be etched. So this concludes it for the grayscale lithography with the NanoFrazor, but another really cool feature of this technology is the markerless overlay. So what this means is that we do not require markers on our devices to find the features, because we could simply use the cantilever tip of the NanoFrazor in the cold mode, scan over the sample, and find the features of choice. And this is important because we know that for more complex device fabrication, we often require to align patterns onto existing topographies or existing other patterns on the sample. And if we look back to standard techniques of lithography like E-beam or photolitho, all of these require markers. But for certain features, it could be quite difficult to do this marker alignment. For example, for nanowires, it could prove to be quite difficult to align them with the other lithography techniques just by virtue of the random positioning of these nanowires on the sample. But with the NanoFrazor, this is not a problem. So what happens is that we take our sample, we coat it with our resist of choice and with the stacks that I showed you previously. And what's cool is that we can detect these nanowires and these 2D material flakes even under thick resists. And you can see examples of that here, always to the left side. You can see how we can detect the topography of a nanowire under PPA. So this is an image that was taken in C2 with the NanoFrazor. And then once we have this topography image, we can simply drag and drop our design of choice. So in this case, it's electrodes contacting the nanowire. We simply drag and drop these designs, overlay them on the existing topography image that we see on our software screen, and then begin the patterning and continue with the pattern transfer just as we described before. So here you can see all the outputs of this markerless overlay method. And I have to say that in most of these examples, we were able to contact nanowires even using the simple bilayer resist stack liftoff method. So it's quite a powerful tool. I'd also like to mention that we actually have a webinar going into more detail about this markerless overlay method. It's always easier to see a live demonstration of this method than to just hear it in words. So I invite you all to visit the HIMT YouTube channel and look up markerless overlay as well. So using this method in combination with our damage-free patterning technique, we can achieve quite innovative devices, nano devices in particular, and you can see some examples of it here. And the reason I say damage-free patterning is because we are not charging our sample of choice. We are not bombarding it with electrons or other particles, so we can contact nanowires and 2D material flakes without any damage induced to the sample. And in doing so, we can achieve new nano devices such as nanowire transistors, but this time with record device performances. You can see that exemplified in the plot here. And in this case, we are getting close to the theoretical limit of the subthreshold slope for these devices. So the limit of 60 millivolts per decade, and we do that at room temperatures as well. So now that you've seen some examples of the high resolution patterning and the different pattern transfer methods, it's good to come back to our previously mentioned method of also writing with the direct laser writer head. So when we combine these two methods, we say that we are doing mix and match lithography, and we can do both high resolution, smaller patterning, and lower resolution, very large area patterning using the same NanoFrazor Explore system on the same sample with the same resist material system. And you can see an example of this here. You can see that the larger tens of microns big features are written with the laser on top of the PPA, and then the finer features are done with the cantilever tip. Of course, here we also use the markerless overlay method to overlay the fine features on top of the existing larger ones. And then we use the cantilever tip in the cold mode and scan over this entire region to read what we've written with both the laser and the cantilever tip. And you get this output topography image in the software itself. So using this method, we are also compatible with other lithography techniques, and you can see an example of this here. So here we are combining many unique features of the NanoFrazor. So starting with the markerless overlay method, and looking at this image here, you see many large patterns that were done with e-beam lithography. Now, if I focus on this green square, what we did here is we overlaid a laser pattern, which was done with the NanoFrazor, and we connected it to the existing e-beam markers. And we did that through our markerless overlay technique. And if we zoom in even further to this blue rectangular area, you'll see that we were able to write really high resolution features with the NanoFrazor cantilever tip. So we can do markerless overlay, mix and match of high resolution and larger area, lower resolution features, and also make it compatible with existing lithography methods. So now you can see how the laser can be useful for really large area patterning, but the downfall here is that, of course, we are losing resolution. So we are talking about a lower limit of around 1 micron when we use the laser. But if we think a bit ahead and think about how we can have high resolution, large area features, then it's natural to think of a multi-tip extension to our product. You can see examples of it here. So we are already working on this prototype, decapite cantilever, and we've already demonstrated how we can use each one of these tips sequentially in a decapite prototype, and we're planning on having a decapite which is capable of full parallel patterning in 2024. So yeah, keep an eye on this product. And with this, I'd like to conclude my presentation. I hope I was able to nicely demonstrate all of these different unique features of the NanoFrazor technology, and I hope I was able to show you how you can use this method for rapid prototyping of different devices and how you can achieve unique applications with the NanoFrazor.